Hey, this is Mr. Mitchell with another video. Today we're going to talk about specific heat. We'd mentioned specific heat in the last video. Specific heat technically is the amount of heat energy that will raise the temperature of 1 kilogram of one substance by 1 degree Kelvin. And you'll find out later it could be 1 degree Celsius, or maybe you're finding it out now. The lower the specific heat, the better the conductor the item is. Now, specific heat, this is the formula. However, specific heat is this constant right here in the formula. What Q stands for is the amount of heat. Now, the amount of heat is going to be measured in joules. The amount of heat is going to be measured in joules, and of course you have the mass will be in kilograms, but it could be in grams, and you may be wondering why you can have temperature in either Kelvin or Celsius, why you can have mass in either grams or kilograms, and it's because this formula is not like most formulas. This formula is a lot more like the Newton's second law formula. Force equals mass times acceleration. Whenever we talked about force equals mass times acceleration, we talked about the principle of this formula. The principle of this formula was that you have more force when you have a heavier object. Whenever you have an object that is accelerating more, I believe we talked about a bus and a little bitty Volkswagen Beetle, that if you have the heavier object, the bus, it would have more force. You may remember that we talked a lot about the principle of that formula before we even put any numbers in there. Kind of the same thing here with this specific heat formula. This is just as much for the principle of the whole thing as it is for putting numbers in. Sure, at the end of this video, we're going to put some numbers in and find how much heat we're producing and find what the specific heat is. But here's the basic relationship. You get more energy the higher temperature the object is, and the more mass the object has, and depending upon how much it accepts heat. That's what this C, specific heat, will tell us. You may remember that the conductors, the ones that have the low specific heat, are the ones that, well, they're conductors. They absorb heat better. The things that are very high, like water or liquids, well, they have a very high specific heat, and they just don't conduct as well as the solids do. That's why this fish loves the specific heat capacity of water, because it could be 90 degrees outside in the air, but the water it'll take a long time for this water to actually get to 90 degrees. So this is the specific heat formula, even though specific heat is right here, and it's more on principle than it is actual stuff in there. But there are a couple of big things you need to know about specific heat and how it can help us. Here we have the specific heat formula and how we just moved everything around to show when we don't know what the specific heat is. And that is one of the big advantages of specific heat, is that one of the advantages is you can take an unidentified an unidentified object and figure out what it is by what the specific heat is. Yes, you can try to measure the specific heat. Now let me go ahead and tell you. This is a diagram of going from a solid to a liquid and from a liquid to a gas, and you can see we have temperature and energy. Whenever you're finding the specific heat of something, it does not need to change states from solid to liquid or liquid to gas, because that messes up the temperature. You can see what happens. You have a uniform amount of temperature and energy put in, but once it hits that stage between solid and liquid, like ice to water, then you have to put more energy in to actually change the temperature up. So, as far as this video is concerned, specific heat is going to be when you do not change phases. Sure, we can figure it out a different way, but that's what we're going to have for this particular video for our understanding. And here's a column of specific heats. Look at the things that are lower: mercury, tungsten, platinum, lead. All of these are metals right here. Look at some of the things that are higher: water, ethanol, seawater. These are some liquids. Notice, interesting enough here, ice is made of water, of course, but ice has a much lower specific heat than water does. So ice is much better of a conductor of heat than water is, just because it is a solid. And it's all because of the molecules. A solid's molecules are much more packed together than a liquid's molecules is. When things are packed together more, that means you have more of a transfer of heat you can have. Now I have this milk over here because you have specific heat measured in per unit mass. So the specific heat of a gallon of milk is equal to the specific heat of a quart of milk. A specific heat of a gallon of a whole ocean full of water is the same as it is just a cup full of ocean water if you have the same stuff happens to be in it. So that's a little bit about specific heat. Now let's go to this diagram right here. Let me show you how you find the specific heat of stuff. And here's our normal formula. Here's our normal formula. Let's say we have this test tube that is bringing to boil 100 degrees Celsius. Is bringing it to boil. So let's say this is boiling. I know it doesn't show it right here. But the reason you would boil is because you want the object inside the test tube to be the same heat as the water is. You want this, and they call it copper rivets right here, just a little substance of copper down here. You want this copper to be really, really hot. Why? So you can know what the temperature is. It's hard to get a thermometer amongst the hard of anything solid. So we're going to make it surroundings 100 degrees Celsius so it can be 100 degrees Celsius. That's the whole purpose of it. So once we get this copper to 100 degrees Celsius, then we're going to put it in our water. Now you may remember, specific heat is how much energy does it take to get a mass of substance to increase the temperature by 1 degree. So if we can increase the temperature of the water by putting this hot stuff in it, then that shows you the specific heat, or you can calculate the specific heat of this. If this conducts heat very well, then it would raise the temperature a lot. If this doesn't conduct heat very well, then it won't raise the temperature very much. So what happened is, I'm taking the numbers from when somebody else did this. You had 15 grams of copper, and it increased the water temperature by 1.02 degrees. We had 100 grams of water. We had 50 grams of copper. Notice it's not kilograms. We do not have to convert that to kilograms because it's the principle of it. It's just, if you start out in grams, you got to keep it in grams. Notice this is not in Kelvin, but if you start out in Celsius, you got to stay in Celsius. So long story short, here we're taking the MC delta T of copper and the MC delta T of water. We should be able to equal those out. And by doing so, you have the 15 grams of copper. The change of temperature in copper was 100 degrees down to 26.02 degrees. This started at 25. That's how, see how it increased it by 1.02. So we put that on this side. C is the constant that we're looking for. We put the 100 grams of water, the 1.0 temperature change. What is this? This, according to our chart, is what water is on specific heat. See? So we just put that right in there because we knew that. So just doing a basic algebraic equation, we multiply this and this, ended up with that. We need to solve for C, and C ended up with 384.76. Were we close to what it normally is, hey, we were close. So what you can do is by finding the specific heat, you can eliminate all these other things as to what this is. The substance could be this, the substance could be one of these, and if you have an unidentified substance, then you can do this experiment here. Unidentified substance is the bottom here. You can transfer it over, measure the temperature, and you can find roughly what the specific heat is. And that's pretty handy right there. And finding out what an unidentified object is. Hey, why don't we do some practice with this formula? Like I said, we do have some formula stuff that we do with this, just like force equals mass times acceleration. Here you have 755 grams of zinc. 755 grams is going to be the mass. Times C. What would C be? Well, let's look on this chart. And you can find this pretty much anywhere. 380 would be here. Well, I say anywhere. Just Google search it. You can find these. And as a result, that's why you mostly find energy as opposed to finding these units of C here, because they're on the internet. 300K minus 200K is 100K. And I think we might have enough time to multiply this all out. So 755 times 380 times 100. So let's go with 755 times 380 times 100 equals 28,690,000. So that's a lot of energy right there. 28,690,000 joules. Joules is exactly what you have here. Okay, now for our last one, let's find the specific heat of something. You can see I have C already down here because I know that's what we have to find. A bolt, this is a vanadium bolt, not a lightning bolt, gives up 4,000 joules of energy as it drops 2 degrees Kelvin, or 2 Kelvin. If a bolt's mass is 4.5 grams, what's its specific heat? So you can see we are trying to find specific heat. What is Q? It's the energy, and you can see that this energy is up here. The energy, you may remember, is measured in joules. So what would be the M? Mass is 4.5 grams. And it drops, change of temperature is 2 Kelvin. Remember, it can stay Kelvin. It doesn't have to be Celsius as long as it sticks with Kelvin. So we have 4,000 over, let's see, 2 times 4.9, that would have to be 9. You got joules here. You got grams times Kelvin here. So what is 4,000 divided by 9? Clear that. 4,000 divided by 9 equals, okay, we got 444. That would be 444. Now, let's see what the units are. Now, you probably have deducted that it's going to be joules over grams times Kelvin, and you can kind of confirm that from the fact that we've got some crazy units right here. In fact, negative subscripts right here. So don't get all bogged down with the units of specific heat. It has units, but you can see it even has some strange units that they are. But hopefully you are able to calculate whenever you need to specific heat and energy. And hopefully you can also see that this is on principle as much as it is calculation. MC delta T. Sign off.